26.4 is about diffraction. And if you remember back from when we studied waves earlier, diffraction is that spreading out of a wave anytime it passes through an opening or an aperture, or anytime it goes around a barrier. And one of the results of that is that diffraction also produces what we call interference patterns. There's really not a difference between what we've been calling twin slit interference, and we're going to talk about multiple slit interference, and diffraction patterns, at least as far as what the real cause is. And one of the simplest ways to see a diffraction pattern is if you'll take your thumb and your index finger and hold them really close together, and you point them towards the light source. I'm going to point mine towards this window, and you look right through them. If you get them really, really close together, in the middle, you can actually see sometimes stripes like light and dark fringes. In fact, when I do it right here, I can only see the one, but I can see a decided dark pattern right in the middle. Okay. Sometimes you can see even more. So what's going on there? If we think back to geometric optics says, you know, if we have a shadow and we block the light, then that shadow should be really sharp and clear. But it's really not. If we could look at a shadow up close, what we would see is, and there's some photographs in your textbook you should look at, that the edges of a shadow actually are almost striped looking with these interference patterns caused by diffraction. Okay. Section 26.5, which is the one we're going to really spend our time on, deals with the rules for single slit diffraction. So when we have two, we call it a twin slit interference pattern, but now that it's one, we call it a single slit diffraction pattern. But they're both caused by Huygens principle, that light spreads out in wavelets. If I have a screen or a sheet, and I cut in that a single slit of some width A, and I shine a bunch of parallel light rays. If all those lights are coming perfectly parallel, our intuition says that on the other side here, it should make a shadow essentially. Here's where the bright light gets through, and everything else would be dark. That's what the ray model tells us will happen. But what we see in fact happening is we have a very large central bright fringe, and then we have these smaller ones. They're less bright, and they're not as wide as that central one, but they're there. So what's going on? Well, it's basically what we call a diffraction pattern. Why in the world would we get diffraction patterns? Well, in a way, if this is a width, a slit of any width, remember when we did twin slits? We'd have something like this, and you go, oh, the waves are spreading out, and these waves are spreading out, and by the time they reach over here, you got these light and bright dark stripes. Well, essentially, a single slit does the same thing, because a single slit can be treated like a point source here and a point source here, except you'd have to treat it like lots of point sources, and they all interfere with each other, producing this pattern. The mathematics of the pattern is very, very similar to what we had with twin slits, and I do suggest you look at your textbook and look at that. But when you get finished, you're going to have formulas that look very, very familiar. The destructive interference which is what we normally talk about when we talk about single slit diffraction, occurs when sine theta equals m lambda over a. We know that m is an integer and a is equal to the slit width, and y is equal to r times m lambda over a. You'll notice that when a gets larger, this is going to push those spacing much closer together. If we were to think about the intensity, and I could draw it the way the picture was, the picture when I drew the slits looks something like this. You have the bright central fringe, and then a lesser fringe, and then a lesser fringe. And here's the bright central fringe on the other side. This was the center. This is the central bright spot. So this is Y1, and this is Y2. So that formula is telling us where those dark fringes are. If we knew how far away, the other way you can approach it, we can actually look for what the angular dispersion is too. So we'll work problem or two. This problem is found in your textbook on page 855, problem 28. It tells us we have light from a red laser, and then it has a wavelength of 633 nanometers. We have a slit, a single slit, and it has a width A. That is 0.350 millimeters. And we have a screen that is located a distance of 3 meters from the source, or from this slit. And the first question they want us to answer is, what is the width of the central bright fringe? When they want the width of the central fringe, what they're saying is, we know the pattern looks like this. How far is it from here to here? That's the distance they're looking for. The distance between those two minimums is the width of the central fringe. So we just need to find the location of y1. That's 0. So y1 is equal to r m lambda over a. That's going to tell us where the first minimum is located at. Where is this? And it's going to measure it, of course, from the center. So 3, m is 1, lambda is 633 nanometers, so times 10 to the negative 9. And the slit width is in millimeters, so 0.350 times 10 to the negative 3. So I've used my formula. Y1, when I punch in all the buttons, is 0.00543 meters, or 5.43 millimeters. You want to do that. So the width is actually double that, because it's from Y1 to Y1. So the answer is going to be double that. It's 0.0108, or 09 actually, by the time we round it. It's going to be 86. Or that's about 10.9 millimeters. That's the width of that central bright fringe. Part B on that question asks about the width of the first bright fringe after the central fringe. So how wide is this one? We go from here to here. Well, we already know the location of Y1. We need to find the location of Y2, and that will give us, we can figure how wide that next bright fringe is going to be. Well, Y2 is going to just be M equals 2 there. Be sure that you know nanometers is 10 to the negative 9 and millimeters is 10 to the negative 3. And we find out that Y2 is located at 0.01085. But if we subtract Y1, which is 0.00543, this whole thing comes out to be 0.005. That's enough significant digits, I think, or about 5.4 millimeters. So what we find is this bright fringe is about half the width of that central bright fringe. And that also seems to make good sense with what we understand. So single slit diffraction, the formulas are different in the sense that for a twin slit, this is a location of a maximum or bright spot, but for single slit, this formula is a location or for a minimum. So just pay close attention when you're using the problems, but those formulas are all on the formula sheet, so you shouldn't have too much trouble. We've got one more section I want to go over in the next video, and that's going to be diffraction gratings or multiple slits.